NASA just started a clock, a 30-minute countdown to the potential end of the modern world. Not a movie plot, not a distant threat, a new operational reality. Deep inside the agency, an artificial intelligence named Dagger is watching the sun, and it has one job: to give us exactly half an hour of advance notice before a wave of invisible energy fries our power grid. 30 minutes to unplug a civilization. This is not a prediction. This is a warning. A formal acknowledgement that a single, perfectly aimed solar storm has the power to destroy the high-voltage transformers that are the absolute bedrock of American life, knocking out power for not days, but for months, possibly years. And here is the part nobody is talking about. The grid is only the first domino. The second is the internet, a global physical network that has a fatal flaw buried deep beneath the ocean, a flaw most engineers never even knew existed until one scientist proved it was real. Before we chart the path of this single point of failure, let me know in the comments if you had a 30-minute, confirmed by NASA warning that the grid was about to go down for good. What is the one thing you would do first? The answers might be more important than you think. We cover these stories because they represent the hidden fractures in our world, and if this kind of reporting is something you value, please take a moment to subscribe. An enormous percentage of people who find our videos helpful simply forget to hit the button. It is the only way to guarantee you see the briefings that follow this one. It's critical for our channel and, more importantly, for keeping you informed. Let's begin. To understand the threat, you have to forget everything you think you know about solar flares. A flare is a flash of light. It travels at the speed of light, reaching us in 8 minutes, capable of causing radio blackouts. Annoying for pilots, but not catastrophic. The real killer has a different name: a coronal mass ejection, or CME. This is not light. This is a physical object, a billion-ton cloud of magnetized plasma, protons and electrons, belched out from the sun, traveling hundreds of thousands of miles per hour through space. If Earth is in its path, that cloud of matter and magnetism will slam directly into our planet's protective shield, the magnetosphere. The impact warps, compresses, and violently shakes our planet's magnetic field. And that rapid shaking is what induces electricity in the ground beneath our feet. A rogue current that our world was never built to handle. We know this because it has happened before. September 1st, 1859, a British astronomer named Richard Carrington is in his private observatory, sketching sunspots. Suddenly, he sees an impossibly bright white light erupt from the sun's surface. A flash so intense he thinks the filter on his telescope has broken. It lasts 5 minutes. 18 hours later, the CME that followed that flash hit the Earth. The result was the most intense geomagnetic storm in recorded history. The Carrington event. The sky erupted in auroras, so bright people in the Rocky Mountains woke up, thinking it was dawn. You could read a newspaper by the light of the aurora in New England. Gold miners reported seeing lights so vivid they started making breakfast. But the real story was happening on the wires. The world's only piece of high-tech infrastructure at the time was the telegraph system, a network of long copper wires stretched across continents. When the storm hit, these wires became giant antennas. Geomagnetically Induced Currents, GICs, surged through them. Telegraph paper spontaneously caught fire. Pylons threw sparks. Operators received electric shocks from their own equipment. The system went haywire. But then, something strange happened. Something that should be impossible. Telegraph operators in Boston and Portland, stunned by the chaos, disconnected their batteries from the lines. The power source was cut. And yet, the messages kept flowing. For 2 hours, they continued communicating using only the raw, free power generated by the storm itself. The auroral current, they called it. It was a scientific curiosity, a steampunk anomaly, but it was also a warning, a demonstration of the raw power lurking in the space between us and the sun. In 1859, the only consequence was a few fried telegraph offices. Today, the consequences would be measured in trillions of dollars and millions of lives. Because we have wrapped the entire planet in a web of long metal conductors, and we call it the power grid. March 13th, 1989. A severe G5 solar storm, far weaker than the Carrington event, slams into Earth. In Quebec, Canada, the region's geology, ancient resistive igneous rock, acts as an insulator, preventing the storm's induced currents from dissipating harmlessly into the Earth. Instead, that electricity searched for the path of least resistance. It found the high-voltage transmission lines of the Hydro-Quebec power grid. Power transformers are built for alternating current. AC, the electricity from a solar storm, is a bastardized form of direct current. DC, pushing DC electricity into an AC transformer is like pouring sand into a jet engine. The transformer's core instantly saturates. It can no longer regulate voltage. It just gets hot, dangerously hot. At 2:44 a.m., the protective relays on the Hydro-Quebec grid started to trip, one after another, in a cascading failure. The system was trying to save itself, but the surge was everywhere at once. The entire grid collapsed. It took exactly 90 seconds. In less time than it takes to boil water, 6 million people were plunged into darkness. The Montreal Metro shut down, trapping commuters. The airport closed. Businesses, homes, stoplights, all gone. The blackout lasted 9 hours. Dr. David Bottler, a Canadian space weather expert, called it the biggest geomagnetic storm of the space age, not a what-if. A documented failure of a modern grid under solar assault. And this is the lesson that should stop you cold. The 1989 storm was a warning shot, a moderately strong storm that happened to hit a geologically vulnerable area. What happens when a truly massive storm hits a nation like the United States, whose grid is far more complex, interconnected, and fragile? A 2013 report from the insurance market Lloyd's of London tried to calculate the cost. Their estimate for a Carrington-level event today wasn't just about repairs. It was about the collapse of everything else. The number they landed on was up to $2.6 trillion. A 2017 study from Cambridge University put the daily economic loss to the U.S. alone at $41.5 billion. Plus, another $7 billion every single day in international supply chain disruptions. These are not numbers. They are a prophecy of paralysis. The core of the problem is not that the power would go out. It's that in many places, it wouldn't come back on for a very, very long time. The giant high-voltage transformers that connect generating stations to the national grid are the system's vital organs. They are also its most vulnerable component. When a GIC surge melts their copper windings, they aren't repaired. They are destroyed. Permanently, these are not items you buy off the shelf at Home Depot. A single one can be the size of a small house, weigh over 400 tons, and cost millions of dollars. They are custom-built, often taking 12 to 24 months from order to delivery. There is no strategic reserve of these transformers sitting in a warehouse somewhere. If a storm were to destroy hundreds of them across the East Coast, the Pacific Northwest, or the Midwest, all regions at high geomagnetic risk, the replacement process would be a logistical nightmare measured in years. NOAA, the National Oceanic and Atmospheric Administration, estimates that in a worst-case scenario, between 20 and 40 million Americans could be left without power for a period ranging from 16 days to 2 years. 2 years. Imagine your city, your state, with no electricity for 2 years. No refrigeration, no clean water pumped to your home, no sanitation systems, no ATMs, no gas pumps, no internet, no communication. It is a regression to a pre-industrial existence. Overnight, the only thing more terrifying than this scenario is how close it has already come to happening. On July 23, 2012, a colossal CME, one that scientists confirmed was at least as powerful as the 1859 Carrington event, erupted from the far side of the sun. It rocketed out into space, a wave of planetary destruction. It barreled through the solar system and crossed the exact orbital path of Earth. But Earth wasn't there. We had passed that exact point in space just 9 days earlier. We missed a civilization-ending catastrophe by about 1 week of orbital motion. We dodged a cosmic bullet fired from 93 million miles away. NASA's Stereo A spacecraft was in the line of fire and recorded the whole event, giving scientists a terrifyingly clear picture of what we had just avoided. Daniel Baker, a space weather expert at the University of Colorado, stated that had it hit, we would still be picking up the pieces. This was not a once-in-a-millennium fluke. It was a roll of the celestial dice. And the sun is rolling those dice more and more frequently. We are currently in Solar Cycle 25, the sun's 11-year cycle of activity, which began in December 2019. The official Solar Cycle 25 prediction panel, a group of experts from NASA and NOAA, initially forecasted a weak cycle, peaking with around 115 sunspots. They were wrong, catastrophically wrong. By mid-2024, daily sunspot counts were regularly exceeding 250. The sun is far more active, far more violent than anyone predicted. And more sunspots mean more flares and more CMEs. The chances of another Earth-directed, Carrington-class event are not low. They are simply a matter of time. If you feel this information is important, take a second to hit the like button and share this documentary with your family. Understanding this threat is the first step, and most people have never even heard of it. But the power grid is only half the story. The comfortable narrative has always been that even if the grid fails, the internet is more resilient. It is decentralized. It has backups. That narrative is a fantasy. Because we made the exact same mistake with the internet that we made with the power grid. We ran a very long wire through a very dangerous place. In August 2021, a computer science professor at Irvine named Dr. Sanjitha Abdu-Jyothi presented a paper at the SIGCOMM Data Communication Conference. The title of her paper was Solar Superstorms, Planning for an Internet Apocalypse. The term was not hyperbole. It was a technical conclusion based on a vulnerability she had discovered hiding in plain sight on the floor of the ocean. The global internet is not a cloud. It is not wireless. It is a physical network of over 400 submarine fiber optic cables stretching hundreds of thousands of miles across the seabed, connecting continents. Many people mistakenly believe these cables themselves are vulnerable. They are not. The glass fibers that carry data as pulses of light are immune to geomagnetic storms. They are insulators. The vulnerability is in the equipment used to boost the signal. As light travels through a fiber optic cable, the signal degrades. To compensate, the cables are fitted with repeaters or amplifiers at regular intervals, roughly every 50 to 80 kilometers, or about every 50 miles. These repeaters are sophisticated electronic devices, and they need power. That power is delivered by a single copper conductor cable that runs the entire length of the submarine line, right alongside the fiber optics. A copper wire, thousands of miles long, lying on the ocean floor. It is a perfect antenna for geomagnetically induced currents. Dr. Abdu-Jyothi realized that a powerful CME could induce a massive current in this conductor. A current strong enough to fry the sensitive electronics inside every single repeater along the line, all at once. It wouldn't damage the fiber itself, but it would kill the components that make the fiber useful. A cable with dead repeaters is just a dark, useless strand of glass. And here is the critical part. This danger is not distributed equally. The effects of a geomagnetic storm are most intense at higher latitudes, closer to the planet's magnetic poles. The highest concentration of vulnerable, long-distance submarine cables is in the North Atlantic, connecting the powerhouse economies of North America and Europe. Cables crossing the Pacific are generally shorter and at lower latitudes, making them more resilient. Asia is substantially less at risk than the United States. A severe storm could, in a matter of minutes, sever the primary data connections between the two most important economic continents on Earth. The result would not be a slower internet. It would be a partitioned internet. Continents would be cut off from each other. Financial markets would disconnect. Cloud services hosted on the other side of the ocean would vanish. The global logistics network that depends on constant data flow would cease to function. Dr. Abdu-Jyothi put it plainly, our infrastructure is not prepared for a large-scale solar event. We were given a preview of this fragility just recently. On May 10, 2024, a massive sunspot cluster, big enough to be seen from Earth without a telescope, designated AR3664, unleashed a series of powerful CMEs. They merged into a cannibal CME and slammed into our planet, triggering the first G5 extreme geomagnetic storm since the Halloween storms of 2003. Social media was flooded with stunning photos of the aurora borealis seen as far south as Puerto Rico and Mexico. It was beautiful, but for some, it was chaos. Across the American Midwest, farmers were in the middle of their critical planting season. Modern agriculture is a high-tech operation. Many large farms rely on tractors equipped with precision GPs, allowing for autonomous navigation and planting with centimeter-level accuracy. But during the storm, that GPS system failed. The storm's impact on the ionosphere degraded the signal, rendering the precision guidance useless. John Deere tractors, some of the most advanced farming machines on the planet, sat idle in their fields, unable to plant. The storm didn't just create pretty lights, it directly interfered with the American food supply chain. It was a minor disruption, quickly resolved. But it was a profound demonstration of how deeply intertwined our most basic systems are with the delicate stability of near-Earth space. The timing of the storm was almost poetic. As the G5 event unfolded, NASA was in the middle of a planned training exercise with FEMA and other government agencies. The goal of the simulation? To run through a hypothetical scenario of a major space weather event and test their response plans. Jamie Favors, NASA's Space Weather Program Director, remarked on the irony. The plan was to run through a hypothetical scenario, then their simulation turned into reality. The universe, it seems, has a dark sense of humor. And it was tired of being ignored. Faced with this escalating reality, a more violent sun, a fragile grid, a vulnerable internet, and a near miss that proved the stakes, NASA and its partners knew they couldn't just keep issuing vague warnings. They needed a tool. They needed an alarm bell. They built Dagger. The name sounds like a weapon, but the acronym stands for Deep Learning Geomagnetic Perturbation. Developed by a team at the Frontier Development Lab, a collaboration between NASA, the U.S. Geological Survey, and the Department of Energy, Dagger is a new kind of weapon. A defensive one. It is an artificial intelligence model trained on an ocean of data, decades of solar wind measurements from satellites like ACE and WIND, combined with ground-based magnetometer readings from all over the world. Its purpose is not to predict when a CME will leave the sun. We already have that. Satellites give us 1 to 4 days of notice that a storm is on its way. Dagger's job is far more difficult and far more important. Its job is to predict what will happen in the 30 minutes after the CME hits the magnetosphere. When that cloud of plasma strikes, Dagger analyzes the real-time data from satellites positioned between the Earth and the Sun. In less than a second, its neural network calculates how the magnetic field will deform and, crucially, where on the surface of the Earth the dangerous geomagnetically induced currents will be strongest. It can pinpoint the specific regions, the specific substations that are about to get hit, and it does this with exactly 30 minutes of lead time. Vishal Upendran, the lead author of the paper unveiling the AI, said it makes it possible to make rapid and accurate global predictions and informed decisions in the event of a solar storm, thereby minimizing, or even preventing, devastation to modern society. It is a monumental achievement, but it also presents a terrifying new reality. We now have a countdown clock. An official, AI-driven, 30-minute warning before the lights go out. I know I'm asking again, but the analytics show that less than 20% of the people who watch this far are subscribed. If you believe this reporting is providing value, please take a single second and click the subscribe button. It ensures we can keep making these documentaries. Thank you. So what can you do with 30 minutes? You cannot build new transformers. You cannot harden the grid. You cannot reinforce the thousands of miles of submarine cable. With 30 minutes, power grid operators can do only one thing: start switching things off. They can try to sectionalize the grid, isolating vulnerable areas to prevent a cascading failure like the one in Quebec. They can take key transformers offline, hoping that a controlled shutdown is better than an uncontrolled burnout. Telecom companies could try to power down their submarine repeaters. It's a desperate, last-ditch effort to save the hardware. A planetary-scale attempt to pull the plug before the surge arrives. But will it work? Will there be enough time? Will the right decisions be made in the heat of the moment, with the fate of the nation on the line? The existence of Dagger is both a comfort and a terrifying indictment. It proves that the threat is now considered so immediate, so real. that the best minds at NASA had to build a doomsday clock just to give us a fighting chance. But an alarm is not a shield. The quiet, uncomfortable truth is that we have known about this vulnerability for decades. The 1989 Quebec blackout was an unambiguous wake-up call. The 2003 Halloween storms, which caused a power outage in Sweden and permanently destroyed 12 high-voltage transformers in South Africa, a country thought to be at a safe lower latitude, was another. The 2012 near miss was a final, screaming warning, and yet our grids remain fundamentally unchanged. Why? The answer is brutally simple: cost and scale. To truly harden the North American power grid against a Carrington-level event would be one of the largest and most expensive infrastructure projects in human history. It would involve installing blocking devices on tens of thousands of transformers, redesigning core parts of the grid architecture, and building up a strategic reserve of spare equipment. The price tag would be in the trillions. The timeline would be in the decades. In a world of quarterly earnings reports and 2 to 4 year election cycles, a long-term, high-cost, low-probability, but high-consequence threat is the hardest possible problem to solve. So we don't. We build warning systems instead. We are left in a bizarre paradox. Our technological sophistication has become our greatest vulnerability. The telegraph operators of 1859, faced with an overwhelming surge of natural energy, could simply disconnect their simple batteries and creatively adapt, using the storm's own power to their advantage. Their system was primitive, but robust. Our system is advanced, but brittle. It is a single, continent-spanning machine of unimaginable complexity. So tightly integrated that a failure in one corner can cascade across the entire network in seconds. We cannot simply unplug the batteries. The batteries are the system. And if that system dies, everything else dies with it. The math of this crisis is simple and unforgiving. Solar Cycle 25 is proving to be far more active than predicted, meaning the sun is throwing more CMEs in our direction. Our civilization is more dependent on fragile electrical and data infrastructure than at any point in history. The gap between the known threat and our preparedness is not closing. It is widening. Dagger is running. Its code has been made open source, and officials are urging power operators worldwide to adopt it. It watches the sun, waiting for the surge. But the 30-minute countdown it offers is not the beginning of the solution. It is the end of the time we had to prepare. It is the final, frantic moment before a test that modern civilization has never faced, and which it shows little evidence of being able to pass. The lights of the 1859 aurora were a spectacle. The next time they appear in skies over Florida and Cuba, they won't be a wonder of nature. They will be a funeral shroud for the world we knew. The question is no longer if that 30-minute clock will start.